The single slit diffraction pattern is a really remarkable phenomena that demonstrates the wave nature of light. Is usually the way we think about it is the wave nature of light to see very narrow slits with light passing through them. But of course, it exists for any type of waves, including sound waves or ocean waves. But where does that pattern come from, and can we explain all of the details? Of course, the answer is yes. So what we're going to be looking at here is single slit diffraction, which occurs when a wave is incident on a narrow slit, similar to the size of the wavelength or smaller. And we want to be able to derive the location for the formula of the first and successive minima for the diffraction pattern from a single slit, and understand how that diffraction pattern depends on wavelength and the size of the slit so that we can solve some simple problems. Recall that when we talk about the phenomena of diffraction, we're talking about what happens when a plane wave, seen here on the left with wave fronts that are parallel to each other, moving horizontally along the screen, encounters some sort of barrier that blocks most of the wave. So the wave here is being absorbed by the yellow, but there's a narrow space here that allows the wave to come through. Instead of seeing a narrow plane wave moving forward, what we actually see is that the wave spreads out. It looks like it's coming from a point source here when that slit is very narrow. And when that slit becomes larger, we mostly preserve the plane wave nature. But we do see some spreading, and we see some details in here that look like maybe interference that's taking place. A region here where there's no wave, and a region here where there's a stronger wave. And so this is what we were referring to with diffraction. We're referring to the extent to which an aperture introduces edges to the plane wave. And it helps us think about how energy is directed away from the into what I call the shadow region. So this would be like the shadow region over here behind the yellow, and how much of that energy gets directed outward. And we do want to also understand some of the additional structure that appears due to interference. Important to understanding this is Huygens' model of waves. So Huygens' model of a wave was that any displacement to a continuous medium, like the surface of water or in air, in terms of sound waves, is its own source of disturbances that spread outward like circles. And that's what we're seeing over here on the right. But on the left, we have plane waves. How can these be thought of as circles? Well, if you look at many, many, many adjacent circles that are all starting from, say, these light gray spots, notice that the circular wave fronts add up and overlap very strongly along lines, so they will constructively interfere, producing a wave front similar to what we see with a plane wave. On the other hand, in between, those crests and troughs will overlap and interfere destructively. So we see areas where there is not much disturbance to the medium in between. So Huygens' wavelet model says that we can think of a plane wave as just an infinite number of little wavelets or ripples that are moving outwards in all directions. The other thing that we need to be keeping in mind while we understand where this diffraction pattern comes from is the idea of interference between continuous waves. Unlike interference between, say, wave pulses on a slinky, continuous interference involves waves coming from two different sources that travel slightly different lengths or distances to meet at a single point. You might think of these as circular waves, two sources, but we're only going to be concerned about this particular point here. And what we see is we're going to see in this top image constructive interference, because if we have a maximum where we start, then from source one, we have 1, 2, 3, 4, 5, 6 full wavelengths. So this point is a maximum. And from source two, we have 1, 2, 3, 4, 5, 6, 7 wavelengths. And so this point will be a maximum from source two as well. And as that wave moves forward, this will continue to be a maximum at the same time from source 1 and source 2, a minimum at the same time from source 1 and source 2. So the maxima will be larger, the minima will be larger, and the equilibrium points will be at the same point. This is what's known as constructive interference, and it occurs when the path length, or the distance from the source to the point we're considering, differs by a whole number of wavelengths. This is shown as a whole number of one wavelength different from these two sources of waves with the same phase and with the same frequency. It's a continuous effect. It happens at all moments in time. And you've probably seen a demo where if you have sound coming from two speakers, there are places where it is louder than you would expect from the two sources being added together. Destructive interference occurs when there is a half wavelength, or 1.5 or 2.5 wavelength path difference. Here, source 1, we have 1, 2, 3, 4.5 wavelengths, but source 2 is still 6. 1, 2, 3, 4, 5, 6. What this means is that the wave from source 2 is at a maximum, while the wave from source 1 is at a minimum. And this will continuously cause interference that cancels each other out, because when you add the amplitudes, these will be zero. Half a period later, the amplitudes will be a maximum for source 1 and a minimum for source 2. They'll still cancel out, producing a dead spot here where there is no wave, even though the two sources are sending waves to that location. So we have continuous interference when there's a whole number path length difference, destructive interference when there's a half path difference. Before we get into the derivation, I want to give you the punchline. I want to give you the answer, that in case you decide you're just going to zip away. So the picture that we have here at the bottom is the picture of what happens when a laser is shown at a very narrow slit. Like, imagine an X-Acto knife cutting a slit in a piece of aluminum foil, and we shine a laser at it. Right behind the slit, you'll see a very bright maximum, but off on the side, you'll see a series of minima that are equally spaced. And you'll see a series of maxima that are spaced out as well. So we have minima, 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 and secondary maximum, secondary maximum, secondary maximum. And the key features are that we have this very large central maxima, and then here the units give us 5 thousandths, 10 thousandths, 5 thousandths, 10 thousandths of a radian to the location of the first and second minima. These will be equally spaced angularly. So we're talking about here, 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 here for those minima. So why do we have these additional features, and where are those located? Well, as you play around, and we'll see a simulation later where you can play around with this, diffraction patterns have some dependencies on the size of the slit and also on the wavelength of the light. So if we think of a red light being shown through a slit, and instead we use a blue light, a light with a shorter wavelength, we see the same basic feature: strong central maxima, several minima that seem equally spaced, but the whole thing has become narrower. The angular width of the central maximum, which is defined as the distance between the first minima on the left and the first minima on the right, has become smaller. Here it's about 10 thousandths of a radian. Here it's less. It's maybe 6 thousandths of a radian. On the other hand, if we take that same red laser and we cut a slit that is somewhat wider, you get the same behavior. Wider slits give less diffraction, or narrower central maxima. Generally, the relationship we come up with is that the angle between the central maxima and the first minima can be found from the wavelength and the width of the slit, usually represented with the symbol b. Theta is equal to lambda over b. Generally, This is quite small, but this gives us the angle in radians where we can find this. Notice that angles in radians tend to be around units, like of 1, like a pi over 2 would be 1.5. So to get substantial diffraction where the first minima is, say, zero point 0.1 radians, you need the wavelength to be similar to the size of the slit. If the slit is very wide, you won't see very much diffraction. You won't see a very wide central maxima. On the other hand, if the wavelength is very, very small, you also won't see that. Now we come to the derivation. If you want to look away, it's okay. Probably nobody's going to ask you to do this, but I think it's really fun to look at and try to understand. So what we're looking at here is an exaggerated picture. Here is our slit of width b, and we're looking at how light from the various Huygens wavelet sources along that slit reach a screen where we can see the diffraction pattern created. Obviously, we've drawn the central maxima here. Here's a maxima off on the side, another maxima, and here are the minima in intensity. And we're going to think about why, it isn't in this drawing, but we're going to think of y as being the distance to this first minima to try to understand where that comes from. And what we'll see is that there's a pair of similar triangles here, especially when we think about a small angle approximation, which is that the angle that is made between the horizontal here and the location of y, if we call that theta, we can also construct a triangle here where the length or the distance from this point on the slit and this point on the path here are different by an amount delta. And so that triangle here shows delta as the path length difference from the bottom of the slit, which has to go a little bit further than the light from the top of the slit. You might imagine these to be maybe, say, the maxima. So maybe this is like 46 maxima, and here you have like, I don't know, 52 maxima or something like that, right? So there's a similar triangle here. This angle theta and this angle theta are the same, which means that y over d, that ratio, is the same as delta over b, approximately, as long as the angle is quite small. To understand why at that point, why we might get destructive interference that leads to there being no light at that point, we're going to break the slit into an even number of different wavelet sources. Here the choice has been made to break it into 10. We're going to label the ones on the top of the slit 1, 2, 3, 4, 5 with the letter A, and the ones on the bottom half 1, 2, 3, 4, 5 with the letter B. There's an equal number of sources in the top half and the bottom half. You could do 1,000 different sources if you wanted to and still understand this. In order to get destructive interference, the path difference here has to be half a wavelength, and then the source at A1 and B1 will interfere destructively. What's neat is that if A1 interferes with B1 destructively, canceling it out continuously, then you could shift this whole picture down by one space and have A2 interfere destructively with B2, and A3 interfere destructively with B3, A4 with B4, A5 with B5. And so every source from the top half of the slit has a source that it interferes with destructively in the bottom half of the slit. And so because all the light from the top half interferes destructively with all the light from the bottom half, when this path difference is equal to half a wavelength or 1.5 wavelengths, this is the origin of those minima. As we want the path length to be equal to b over 2 times the sine of theta. We'll use a small angle approximation. You can take a look into the simple harmonic motion topic 9.1 if you need to learn about small angle approximations. But we'll have destructive interference when b over 2 is equal to lambda over 2. Small angle says that b times theta over 2 will be equal to lambda over 2, or theta is equal to lambda over b. And this is going to be at a point, approximately the point where lambda over b is equal to y over d. So this is our condition for destructive interference. The angle theta is equal to lambda over b. And this is exactly what I told you was the punchline from before. The y over d helps us to think about how far apart these are going to be spaced when they land on a screen. And if you notice here, these are evenly spaced when this is projected against a wall and we take a picture of it. But of course, as you move away from, say, 10 degrees, they start to spread out a little bit more. They're no longer evenly spaced because the small angle approximation no longer applies. The same basic argument can be made if we look to where the second and third and fourth minima occur. It's just that instead of breaking it into a top half and a bottom half, we break it into 4 pieces so that the top quarter interferes with the bottom, with the middle quarter, and this middle quarter interferes with the bottom quarter. That gives you the location of the second minima. Break it into 6 pieces, etc. And so the location of additional minima, we'll call those theta n, is equal to the integer multiples of lambda over b. So you can find the first minima at lambda over b for the angle. You can find the second minima at 2 lambda over b, the third minima at 3 lambda over b. Notice that there's actually no equivalent argument for finding where the constructive interference occurs. That's actually much harder, and we can see that it doesn't actually interfere particularly constructively, right? These aren't strong interference peaks, but they are kind of partially, they're about halfway in between the minima. There are a couple of extreme cases to consider. In the case of very, very narrow slits, that is, B is very, very small, the angle theta can become quite large. In fact, larger than pi over 2. And if the location of the first minima is beyond pi over 2, beyond a 90-degree angle, then you're not going to see that minima. And the slit is going to act almost like a point source. That's this example here, where the size of this slit is approximately equal to the wavelength. And we see that the first minima is maybe located out here close to pi over 2, and the wave looks very much like a point source. On the other hand, if you have a very wide slit, you get very little diffraction. You have a quite sharp shadow, and you see minimal spreading of the light. It's almost like the slit doesn't have the effect of causing diffraction. And that would be where B becomes quite large and the diffraction angle becomes quite small. A couple of interesting effects to take a look at here. One is what happens when we have the diffraction of white light through a single slit. You get these pretty rainbow patterns in the secondary maxima, and there really aren't any places where the intensity goes to 0. You can think about that because the angles where you have the minima for red are in a different location for green and for blue. And like is shown in this picture here, you're always going to have some light, but you'll have different colors of light at different locations, so you get this sort of rainbow effect. Another one is Fresnel's spot, also known as the Poisson spot or the Argaro spot, which is if you shine coherent light at a penny or a small sphere, the light inside of the shadow region, right? So this is the shadow of, say, a penny. In the middle, there will be a very bright spot because the distance from each of these edges to the middle is exactly the same. And when the path length is exactly the same, you'll have constructive interference. So right in the middle of a shadow, you get a very strong and small bright spot. This was originally one of the strongest pieces of evidence for the wave model of light, uh, in opposition to Newton's model of light, which said that light was made up of particles. Of course, when we get back to quantum mechanics later, we'll have more to say about this. So those are the quick things to learn about diffraction. Really, there's one important equation, that the angular location of each of the minima, the interference minima, is found at the integer multiples of lambda over b, where b is the slit width. And if you're using a small angle approximation because you don't get very much diffraction, that would be the same thing as equal to the linear spacing divided by the separation between the slit and the screen. We'll see more on this in the next topic 9.3.